introduce Diego Gimenez, who's going to talk about his simulation. It's automation simulation, which actually started out for Abengoa, and he changed his internship job midway through the semester, so we had to do a little bit of fancy footwork in converting it from the actual implementation to a simulation. Diego.
Good morning. As you may know, my name is Diego Gimenez. My project is about wastewater treatment automation for Abengoa Bioenergy of Indiana. And I'm glad, thanks everybody for coming in and enjoying my presentation. Okay, who's Abengoa? Abengoa is an ethanol plant located just northwest from USI. It consumes about 825,000 tons of corn per year. But not only produces ethanol, but it also produces distillers dry grains, DDG, and corn oil as well. Its ethanol capacity is around 90 megagallons per year, and 230,000 tons of DDG per year as well. Abengoa ships all its products by train, truck, and boat. So a little bit overview of this project. The purpose of this project is to provide Abengoa of Indiana with automation treatment for the wastewater. The automation will be done by creating a programming code through 2 phases. And the project will have the following benefits. It will give Abengoa of Indiana a much more stable water treatment, and will also reduce the chemical consumption in the plant, as this will stabilize the system. Our outline for our today's project will be, I'll talk to you guys about wastewater treatment, then a little bit about the background, alternatives and the options anticipated, project goals, main program, then I'll talk about the design process. I'll introduce you to the flow chart as the code was written. Then I will talk about how it was transferred to a ladder logic code to establish a simulation. And then I will talk about the simulation, economic evaluation. I will give a conclusion, my apologies, and then I'll do some recommendations. So the wastewater treatment, first thing we need to know is that it's a biological treatment process. And the process comes from an equalization tank. This equalization tank slows the flow down in order to have a much more constant feed to the microorganisms that are going to digest all the water impurities. For this process, we use urea and sulfuric acid. I will talk about their effects later. And since this is an aerobic system, their oxygen is required. Then the water goes through a clarifier to remove even much more impurities in the water, and then the water is ready to be reused. This is not exactly the type of process that is taking place at that exact tank, but it does give me it does help me to provide a much clearer explanation of how the tank works. So we have influent water coming in. We have a sludge zone, which all impurities in the water. As you may see, we have the aeration chamber for the microorganisms to be in their habitat and make the system aerobic. Then we have the settling zone, and we finally go out for the effluent water that's going to be reused in the process. The wastewater treatment coming to Abengoa has a pH between 6 and 9, and will also leave the water leaving will have the same pH. The COD, the chemical oxygen demand, it's about 1,096, and that's an influent water. And as it comes out, it goes down to 99. That means it's a 91% removal from the influent water. The regular flow is around 245 gallons per minute coming into that tank. And that's how, it's not exact tank from Abengoa. This is what's called a Model R wastewater tank. As you may see, it has the 2 aeration zone, the sludge holding zones, and the clarifier zone, which finally remove all the impurities in the water. As a background, currently Abengoa Energy batch urea and phosphoric acid in gallon batches. Since this is a continuous nature, it is highly inefficient, that therefore much more sophisticated way was approached in order to have a much more regulated chemical addition. Since this is a highly inefficient batching, the natural levels spike at the beginning of the day, and then through the day they decrease rapidly. That's a picture of the urea tank and phosphoric acid tank that are in Abengoa. And all actions will need to be distributed by, will need to be controlled by the distributed control system, DCS, and the program will have to control all the chemical pumps and lines to be activated in order for the process to function. The program also will break the dosing in 24 equal doses in order to have an equal amount of chemical going through the system every hour and have it become a much more stable system. That's what the DCS control board looks like in Abengoa. As you may see, you have the waste equalization tank, which goes to the aerobic waste, and then finally goes to the treated wastewater tank, sorry. So as the project came through, we have a few problems, and with those problems, solutions came along. The first problem was to come up with a pseudocode that will be suitable for the automation, which was addressed by using the most of the one-to-one time with the advisor. And also, as my advisor explained, the project started at Abengoa, but due to employment logistics, this prevented the culmination of the project at the plant. Therefore, we had to show the pseudocode functionality for its civil adaptation. For that, we solved the problem by creating a simulation that was created through a PLC simulation with two programs, RSLogix 5000 and Factory Top View. RSLogix 5000 was used for the ladder logic, which I'll talk about a little later, and the Factory Top View was used to create the HMI, human machine interface. This is the box that we use I used to recreate the program. These boxes were given to me by the USI faculty, and with that proof the functionality of the pseudocode. So alternatives and options as anticipated. Civil code is pseudocode based. What I mean is they have similarities, but they're not quite the same. They have different commands and different way of writing the code as they establish in the system. There was a problem the designer had no civil experience, but I had to create a pseudocode in order to simulate it later on in the project. Then the pseudocode was adapted to the ladder logic via, again, RSLogix 5000. I'll be talking now about project goals. The project have 4 main objectives. First, to test or prove the pseudocode functionality. This will monitor the conditions and diagnose any issues and have a much higher treatment process. Perform all the operations, such as turning on the pumps, opening the lines, closing selective valve, among others. And again, the program will have to break the dosing unit in 24 hours. And this will also have a timer and a counter to specify the program when to stop. Cycles will be done as a 24-hour batch, as a 24 doses batch. Once the counter reaches 24, it resets the whole program and it starts over again. But also, if the counter is not met to 24 yet, the timer will be important because it will establish a 60-minute interval, which will avoid the overdosing in the system. Once it reaches 60 minutes, it will count as one batch in order to keep the system stable. This program should be used in different computers. The control room in Abengoa have, I believe, 4 or 5 different stations which they need to be accessed from. This should also break the, as again, should be able to break the dosing in 24 equal doses, have a timer and a counter, and the counter will reset when the final count is equal to 24 again. That's the sorry, the interface, how it looks in Abengoa for the wastewater treatment. As you may see, they have the blowers which pump the air into the system in order to make it aerobic. And they also have the urea addition and the phosphorate, which are not shown in this page. Phosphoric acid and the urea tank, as I mentioned before, they are connected to the system, and the pumps are connected into the wastewater treatment. They just need to be activated, which that wasn't part of the project since it was already set up. Again, the code was done in 2 phases, and it operates the different requirements, such as lines and the pumps to be activated, and to prove the PLC simulation to test the code functionality. So the flowchart that the designer came up in order to finish the project, we have the start, and we have a numeric entry. The numeric entry will also have a minimum and maximum amount. This is to avoid an operator to come in and maybe input 1,500 gallons, which is an unrealistic number. If the amount is accepted by the program, we'll move down and divide that total amount in 24 equal doses, and the light, an added chemical light will be coming up in order to let the operator know that the process is running. If not, we'll come back and say, display enter chemical amount again, and if it's not correct again, we'll go back again until the criteria is met. From that, we start with the initial conditions. We have the batch counter, my apologies. Batch counter equals 0, batch timer equals 0. The amount added will be 0, and the lines will start opening, and the pump will start again. Will start in order to start pumping the flow. We ask the timer. If the timer is equal to 60, we move along. If not, we get the input from the flow meter, which will also prevent the overdosing. That's kind of like a backup plan in order to have a much more stable system. If the count is less than 60, then we move to batch counter is equal batch counter plus 1. If we're not equal 60, again we get the input from the flow meter. If the flow meter is a good reading, we add the flow meter reading to the amount added in order to keep track of how many gallons is being batched in the system. If it's a bad meter, we display bad meter light, the pumps will shut off, the lines will close, and the program will stop. The program will not be activated and will not run unless a flow meter has been changed and is fully functional. We come back again. If the batch counter, once the batch counter has been taken into account, we ask the system if the batch counter is equal to 24. If it's not, the pump will be off between batches, and then we go back to the process and ask the timer what time we've got on the batching. If the count is equal to 24, then we're done with all the batches. Pump will shut off, the lines will close, and the program will stop. This is a ladder logic example as it was written on the program. As we may see, we have the start button and the system running. These are normally open contacts. That means that whenever they're normally not going to be running unless the button is pressed to make the connection. As you may see, we also have the emergency stop and the batch counter dump beep and the bad flow meter reading. These are normally closed contacts. They will always be running unless the button has been pressed. The connection then it gets interrupted, and it does not prevent the program to run and move to the next run. Once the system is running, we have the total amount equal to 50, and we move it to a display, which will let the operator know how many gallons of chemical is being added in case of being asked. Then we'll divide the dosing by 24, and we will display adding chemical light. The next example talks about the batch time. If the batch time the batch time will be activated. The batch time done bit will activate the batch count to start counting by 1 every time the batch timer is done. The second run, we have a back flow meter reading, which is again is a normally open contact, and if this is not activated, the program will run just normal. But once it's activated, the batch flow will be equal to 0, which will prevent the chemical addition, and the program will not run. For the simulation, again, we created through a ladder logic and factory top view. This is the HMI, human machine interface, that the designer came up with. And we have the equalization tank, the phosphoric tank, and the urea tank. This is how the program will start. Once the treatment has started, as you may see, chemical pumps turn on, the chemical lines are open, and the added chemical light will be displayed, letting the operator know that the process is running. We have the batch flow and the amount of gallons added, which I will be talking about these two in the next slide. The treatment done shows the flow down to 0. There's no more chemical addition. The process has been finished. The amount added, as you may see, equals the total amount entered, and the treatment done light comes up. That lets the operator know the treatment has been done, and in order to start the treatment once again, this treatment will have to get a new input for the next process. If we have a batch flow meter, the batch flow goes to 0, but the amount added is still displayed. This is in case the process is running, and in case the process is running and there all of a sudden a flow meter goes bad. That lets the operator know how many gallons were in that on that system treatment before that flow meter went bad. So the economic evaluation for this project, I had a 1-hour meeting with my advisor every week for 16 weeks. That gets about $1,600. For the student time, I added 240 hours worth of work at $15 an hour. We get a total of $3,600. And the total amount will be $5,200 for this whole project to be completed. The conclusion, the current program does not provide the needs for Abengoa Energy that are needed to meet the process requirements. The new program will provide a much better treatment and a much more stable system. The chemical amount used will be less due to the control dosing through the system and through the process. And the simulation shows the pseudo-coefficient functionality and performance. So recommendations for Abengoa of Indiana, that they need to check what the pump's flow will be in order to make sure that the minimum flow will be met by the pump, because if the pump is not opening and if the pump is getting closed, the program will not run and will cause the same problem and will create a nutritional imbalance on the system. To finalize, I would like to thank everybody that made an important part on this project on me. First, I'd like to thank God. There's nothing possible without it. Without him, from Abengoa of Indiana, I would like to thank plant manager Daryl Sanford, Plant manager Daryl Sanford, plant engineer Jason Beers, Wes Robinson, operations manager, Jason Deakins, operations system manager, and Tim Wimmer, QSC manager. Thanks for trusting me in order to complete this project and give me anything I needed in order to complete it. To my advisor, Dr. Paul Kuhn, he's not only been my advisor for the project, but has also been a great influence through my engineering career. Dr. Jason Hill, he helped me out a lot with the wastewater treatment understanding and how everything takes place in order to have a much more stable system and have a much better project completion. Donna Moore, our assistant secretary, she's always great. She's always providing smiles for everybody, and she's always having the right answers, even if nobody has them. Especially my mom and dad and family that came over from Venezuela to watch my project presentation and my graduation. I appreciate all the support. And do you guys have any questions?
You mentioned the waste strength, the COD of 1096. How does that vary? Is that a constant?
Well, it's not really a constant. That's the chemical oxygen demand on the system, and it will vary as what the strength is in the water coming into the wastewater treatment. The higher the number, the stronger the water is as it's coming inside the tank. This will vary from when they change parameters within the plant or within the process.
And does your dosage of the urea, phosphoric acid, does that vary with the COD?
It sure does because the urea addition, I don't think I mentioned it, my apologies. Urea addition controls the nitrogen, which is a protein or like vitamin for the microorganisms in order to have a much more stable system, and also the phosphoric acid that will be as a phosphate source for them. So the higher the number, we have to add a lot more chemical to it in order to have a much cleaner water. They need more food or nutrients per se in order to clean the water. Also, if you guys are interested, I'll have a simulation screen on the other side of the room if you would like to know or see how the process works as a PLC simulation. Do you guys have any more questions?